Welcome back. Okay, we're going to solve Bernoulli equations. Okay, Bernoulli equations are dy dx plus p of xy equals q of x times y to the r, where our p's and q's are continuous on some function on some interval ab. Okay, and then this is the substitution we're going to make: v equals y to the 1 minus r. Okay, so rather than show you guys what's going to happen, the algebra would get messy if I do it abstractly. So let's just do it immediately for an example. Okay, so an example we got is y, you do it in a different color, y e to the negative 2x plus y to the third dx equals, minus e to the negative 2x dy equals 0. All right, so let's go ahead and solve. First thing we're going to do, we're going to get it into the right form. So dy dx, doing a little bit of algebra. I'm going to move this over to the other side. Sorry, this over to the other side, and then divide by that. So we're going to, divide by that. So we're going to get y e to the negative 2x plus y to the third divided by e to the negative 2x. Okay, I'm going to do a little bit of simplification. Dy dx equals y plus y to the third e to the 2x. Okay, so far okay. I'm sorry, I can't hear you. You guys okay? You understand so far? All right, that's what's up. All right, so our substitution, well, before we substitute, let's get it into the Bernoulli form. Dy dx minus y equals y to the third e to the 2x. Okay, now, maybe we could, we're going to do our substitution. So our r here is 3. So we're going to make the substitution v equals y to the negative 2. Okay. dv dx is then negative 2 y to the negative 3 dy dx. Okay, let me write that as negative 2 over y cubed dy dx. Okay, so what this gives us is that dy dx is actually negative y to the third over 2 dv dx. Okay, so we're going to put this into that little formula. So we're going to have negative y to the third over 2 dv dx. Oops, sorry. I wanted this one. Okay. Minus y equals y to the third e to the 2x. But now, watch what happens. We're going to go ahead and we're going to divide by y to the third, multiply by 2, and change the sign. Okay, so we're going to get dv dx plus 2 over y squared equals negative 2 e to the 2x. So far, okay? Good. Now, look at this. 2 over y squared. But isn't that just 2v? It is. So we're going to write this as dv dx. Just check how much space. Oh, plenty of space. dv dx plus 2v equals negative 2 e to the 2x. Okay. Now, to solve this, we could solve this easily with an integrating factor. Not a special integrating factor, but just the integrating factor technique from week 1 that we did. Okay. So we're going to multiply on both sides by an e to the 2x. Okay. And we got that by taking, of course, the integral of that 2 e to that integral, right? So we're going to get e to the 2x dv dx plus e to the 2x times 2v equals negative 2 e to the 4x. This side condenses into the derivative with respect to x of e to the 2x v equals negative 2 e to the 4x. Integrating both sides. On the left-hand side, you just get rid of the derivative. On the right-hand side, you get, again, e to the 4x divided by 2 with a negative plus a c. Okay, so v of x is going to be negative e to the 2x divided by 2 plus c e to the negative 2x. All right. Just checking. Okay. So v, remember, is 1 over y squared. Okay, and we can solve that to get y. Y of x equals a little bit of algebra magic, the square root of 2 over c e to the negative 2x minus e to the 2x. Okay, now I don't need to worry, like when I did this, there would have been like a 2c over 2 here, but that's going to be the same thing because it just gets sucked into the constant. Okay, so there you have Bernoulli equations. All right, one more video.